Good. So last time we introduced the chapter 6. So it's about chemical bonding. And here I want to spend a couple of minutes to review what we learned last week. Okay. So basically, we can use the Lewis dot symbols to describe the valence electrons of the atoms. For example, we use for this group that only have one valence electron, so we use one dot, right? Like 2, 3, 4, 5, 6, 7, and here 8. And we also introduced the octet rule. So it's about basically it tends to form the full energy, full orbital. Okay, because the full energy levels are very low energy. So using the Lewis dot, we can using this way to describe the reaction process. For example, basically for the metals, they lose one electron to form this kind of anionic compounds. So between the metal cation and the non-metal and iron, they form the anionic bond. Okay. But for the for this covalent compounds, basically for two atoms, they share the electrons, so they form the covalent bond. Like this, in this case, so these two fluorine share 2 electrons. So for each one, it has 8 electrons. And in this case, these two atoms share 2 electrons, so forming the single covalent bond. Okay. They may also share 4 electrons, like this, between carbon and oxygen. Okay, so they form like this kind of double bond. Okay, and in this compound, you can say for each atom, it has 8 electrons, and it is full orbital, so it is stable. The third one is about the triple bond. So in triple bond, the 2 atoms share 6 electrons, to form the triple bond. So this is about the types of the covalent bond. So it may be single bond, double bond, or triple bond. And for bond, it has the bond length. So basically, the triple bond, its bond length is less than that of double bond, and of course, it's shorter than single bond. And then we also introduced the polar covalent bond. So, for example, between these 2 atoms, there are 2 electrons, but these 2 electrons tend to close to the fluorine. So this looks like the fluorine has some negative charge, and the hydrogen has some positive charge. So they form this kind of polar covalent bond. And basically, use this figure to determine what kinds of bonds between two atoms. So basically, we can determine the bond types according to the difference between the difference of in electron activity. So if the difference is zero, this means these two atoms are same. So definitely they form covalent bond. And if the difference is more than two, like this compound. So basically one is metal, another is non-metal. So their differences are more than two, so basically they form anion bond. So this means the electron will be moved from the metal to the non-metal to form the anion bond, and also this kind of compounds are called anion compounds. Yeah.
I have a question.
Yeah.
Although it's in the previous slides, not this one there.
This one, no, okay.
No. Like
Back, right?
This slide here.
This one?
Yes.
Yeah.
For lithium.
Yeah.
When you react with the fluoride, or when it formed lithium fluoride, it says, when it lost the electron, yes, don't.
So this is lose one electron.
That's the problem. Yeah, when it loses that electron,
Yeah.
it remains with two electrons. Like it's.
Yeah, it only has one s two electrons.
Yeah, when it reacts, it loses that electron to the fluoride.
Yeah.
And then it remains with one electron. So those two electrons are not shown in the diagram.
No, why the valence electron? Okay, valence is like ys. It is electron configuration is ys2 ys2 2s1.
Yeah.
So
I'm saying like okay.
You lose the electron from 2s1.
He's saying after you
The configuration remains like this. So with these two electrons, then they're not shown here.
Oh no, you don't need it because here we just show they are valence electron. This ys2 this electron is in orbital, right? In orbital, don't this dot like this. You can see, for example, here, this only from the valence electron. Valence means like, but for example, this is 1s1, right? So this is 2s1, so this is 3s1. Of course, it also has some like ys2, 2s2, right? We don't care. We only like valence, the valence electron. Valence electron, just the most outer orbital electron. So we don't, for this we don't write ys2.
So it becomes wrong when you write them. For example, in the exam, if I put them there, it's wrong.
It's wrong.
It's wrong.
It's wrong. Yes, because this only means there are valence electrons. If you put two dots, right? So this means it has two valence. No, it's valence electron. It's moved, right? So it doesn't have any valence electron. It doesn't have. Okay, so you don't need write any dots. The dots only represent the valence electron. Okay, it is loose its valence electron, so it's nothing. Okay, so here you only write like this. Okay. if you write all electrons around it, it will confuse. Okay. So basically, using this picture, we can determine the bond types of the compounds. And if the difference is between the 0 and the 2, so it means it forms the polar covalent bond. Polar covalent bond. Okay. So in this bond, they share the 2 electrons, but one atom will attract the electrons more than another one. Okay. So we also introduce the resonance structure. Resonance structure means one or two or more Lewis structures to represent the structure. Okay, we also introduced some exceptions to the octet rule. So this means the octet rule cannot explain all compounds. So maybe in the future we can set better theory to explain these compounds. Okay, so this all we learned last time. So here is about the bond and enthalpies and enthalpy changes in reactions. So what is enthalpy change? Enthalpy. So enthalpy is also look like it's also an energy. Okay, it's like if we break a bond in one more of gaseous molecules. The state is gaseous molecules. So this energy is required. It's called like bond enthalpy. Bond is called enthalpy. So this is also called bond enthalpy. Also, I think this is bond enthalpy. So here, to show the bond enthalpy for like H2, hydrogen, chloride, and these kinds of gases. So what does this mean? For example, for hydrogen, H2, if we break the bond, the hydrogen bond, right? So you will need provide 436.4 kilojoule, okay? So this energy is called bond enthalpy, okay?
How does it come about?
How do you get?
How do you get the
Basically from the experiments. Yeah, there are some special experiments to measure, to get the enthalpy.
Okay, so how about what's that H? Delta H, what's H
H
representing?
means just atom. Gases atom, hydrogen.
So that H is no, as in not the hydrogen, but I mean.
This is hydrogen gas,
No,
right?
not the.
Yeah, this hydrogen, right?
Again?
Yeah, we just using this symbol to show
Okay.
to show the
Show
bond
the-
enthalpy sets. Yeah. So all the bond enthalpy are written as H.
Alright.
Okay. Yeah. And here is like 0, right? 0 is like means standard. Standard.
Okay.
Okay.
If it's 1, what does it mean?
What?
If instead of 0, it's 1. What does it
No, basically it's not like 0. Here it's not 0. It's just also together like the degree, right?
Okay.
Also degree, also like 0 and C, right? It's like this. Okay. Yeah. So here we can see, for example, in this case, nitrogen gas, the enthalpy is much higher than others. The reason is because in nitrogen gas is triple bond. Okay, yeah, triple bond also means of course it requires more energy. to break the the nitrogen, this bond, the bonds between the nitrogens. Okay, so basically, for bond and their has so single bond less than double bond, as also less than triple bond. Okay. Okay, so this is about the bond and their pi. Okay, so this table to show some common bond and their pies of this is all about your diatomic molecules. So here we can see, for example, this nitrogen is higher, okay, and for the same group, you can see the fluorine HF, this bond as pi is higher than others. So you see in one group, from up to down, the gel pies decrease. So why? Why in the same group, the bond and gel pies decrease from up to down? So you can see from fluorine is larger than this one, right? Chlorine, then bromine, then iodine. This one is largest one. So why?
Because gases at top, it decreases you could.
So basically, the impact means the energy, right? Energy also means the stable, right? If it is stable, so you need to provide more energy, right?
Yes.
So this means HF is stable than HI. Okay. Yeah, because the distance, bond distance. Basically, we know if the bond distance is short, so this means it's stable. Okay, so you need it requires more energy, and we know HF is much shorter than this one, so this means HF and is hard to be broken. Okay, so it needs more energy, so it has a higher bond and their pi. Okay, so here is to show the how to calculate the average bond and their pi. For example, in water there are two OH bonds. If we break the first one, so you need the energy is 502. Okay. So and then the second one you need 427. So basically we can calculate the average OH bond and their pi is 464. So basically we can see these two times we need to break the OH 2 times, and for these 2 times the energies are different, a little different. Okay. Okay. So after we know the bond and their pi, so we can use the bond and their pi's to calculate the their pi changes in reactions. So for example, basically for a reaction, we have some reactants, right? Reactant molecules, and after the reaction, they form the products. Okay, so basically there are some product molecules. For reactant molecules, we can emit like reaction proceeding by breaking all bonds in the reactants. So at first we just broke all bonds in the reactants. So when they are broken, so they form just the atoms. just atom. So and then we using the gaseous atoms to form all the bonds in the products. So here we can see first step, just break the reactants. So when we break the reactants, we need to provide energy. So this is one energy, right? And when they break, when all them are broken, so they form single atoms. And then these single atoms combine together again to form the new product. And then when they form the new product, they will release energy. So in this process, from the reactants to products, there are two energies, right? So first step, they need to absorb energy. Second step, they will release energy. So, and between the difference of these two energies. So for the difference between these two energies, so this means the enthalpy changes of the reaction. Okay. So basically, there are two kinds of situations. So first, in this case, we can say the energy required is larger than the energy released. So for this energy, after the reaction, it will release energy or absorb more energy. So question, in this case, from the reactants to product, the reaction will release energy or absorb energy. Absorb why?
Because the energy released is less than the energy.
Yes. So this kind of reaction is called endothermic reactions. Okay. Endothermic reactions means they need absorb energy from outside, from environment. Okay. Okay. So in this case, we can say the energy required is less than the energy released. So of course, in this reaction, after this reaction, it will release energy. So this kind of reaction is called exothermic reaction. Okay. So basically, we can use the bond enthalpies to calculate the reaction enthalpies. Okay. So the process like this, for example, for this reaction, hydrogen, the gas hydrogen react with the chloride gas to form the HCl gas. So basically, so this is hydrogen, this is chloride. Okay, we can just first step break the all bonds of the reactants, and then form the new compounds, compound. And also in this reaction, we can say the first step is just break the hydrogen bond, and then break the hydrogen bond and the oxygen bonds, and then they form the OH bonds. And in the first step, we need to provide energy. And the second step, they will release energy. Okay, so here's the question. So use bond enthalpies to calculate the enthalpy changes for this reaction. So this table give you can find the bond enthalpies of the reactants and the products. And also basically how to calculate the enthalpy change is reaction. So we just using the total energy input minus the total energy released. So this means we're using the bond enthalpies of reactants minus those of products. Okay. So using reactants minus the products. So yeah. So question. So we using the reactants, right? Reactants and their parts minus the products. So what are the reactants? Hydrogen and fluoride, right? So what are the bond enthalpy of hydrogen? How much? Yeah, this number, right? Fluorine. Where? This guy, right? And then from here, 2 more of HF. So it means it's for 2 HF bonds, right? Yeah, should time 2. Okay. So how to get the answer? So anyone want to try? Reactants minus the products. Yeah. You want to try?
So reactant is the product.
Is multiplied.
So reactants uses reactants, right? And therefore minus the products.
No, you can use your negative.
So these are reactants. These are products.
If it's negative, then
Then
it's
it's negative.
Sorry, since it's H2.
Yeah, come here. Tell me the show answer.
nothing go. Oh, then never mind.
Yeah, how to? Yeah. This is so using reactants.
So 2 times 5, 6, 8, 1,
2.
2.
Yeah, this is products.
Yeah, so products.
But what is reactant?
What's the. Yeah, this is the reaction. So this. Plus,
Yeah. Plus which one? Fluoride.
Yeah, fluoride. This one.
This one. Yeah.
Vehicle.
What is 150? Why you get this number? How to get this number? Should be this one. And
These are the reactions.
oh, okay. Oh, okay. I see. Okay, this gets problem. But you need to use the reactants minus the products.
Reactive
Reactant minus product.
Reactants minus the products.
Reactant. That's the budget.
I'm just trying to get the figures first. So this
So which ones are the reactants?
this is for product.
Yes.
The reactants.
Product.
Okay.
Reactants.
And if the
Reactants is 593.3.
Yeah.
0.3.
Yeah. So how to calculate?
It's negative.
Then formula is reactants.
Yes, minus the
Minus
products.
So
Yeah. Use this guy minus this one, right?
yeah.
Yeah. What's that?
Okay, you can.
It's exercise.
Okay, good.
So what's
So at least minus, right? So what does this mean?
He said as you go down the group, it becomes
What does this mean? get the electric number. What does this mean? The reaction after the reaction, it will release energy or absorb energy.
Absorb.
Absorb?
Release.
The answer is negative.
Okay, let's try to use logic. If here gives us this.
The number.
The answer is negative. It means it absorbs energy.
It will release energy. So minus, what this means? This means for this system,
That's like.
it will lose energy.
Okay.
Okay? If it's minus, it means it's lose. It's lose energy. Loses energy. Okay? So it means it will release energy. And also we can say the products bond enthalpy is higher than the reactants, right?
Yeah.
So this means when they form the products, they will release more energy. Okay? Okay, good. Oh, how to remove?
That back, the center.
The
Center.
Good. Oh, what?
panic biology.
X.
Okay, good. Okay, so basically, you should remember using the reactants minus the products. Okay. So for hydrogen, reactants, hydrogen, chlorine. And here, because it's 2, so it means there are 2 bonds. Okay, you should have 2. Okay. Yeah, so use the reactants minus the products. Finally get a lactic number. And this means after the reaction, this system lose energy.
Correct.
Lose energy. Okay, so it also is a release energy. So this also means it is easy for this reaction to happen.
Say it.
Right.
What?
Okay, yeah. So that's all for this chapter
What's happening?
and homework. And homework, okay? Not too bad, just only 2 questions.
We did this.
Yeah, I will close it.
Oh no, we didn't do this.
What?
It's okay.
We didn't do it.
Next Friday, give me.
Yeah.
Next Friday, of course, not today.
Next Friday. That's right. Yeah.
Mana? Main. Ni tak fit. I'm saying yes.
Okay, so just now we introduced the chemical bonds, like the types of the chemical bonds, and also how to from the bond enthalpy to calculate the reaction enthalpy, the change of reaction enthalpy. So this chapter we will continue introducing the chemical bonding. But from this chapter, we will learn how to from the chemical bondings to determine the molecular geometries. Okay, talking. Okay. And we also introduce the some theory about the chemical bonds. So The first, basically it includes four parts. The first one is about the valence shell electron pair repulsion model. A little complicated, right? But here, basically, with the valence electron, right? Valence electron means the electrons in the outermost shell, and basically they can repel each other in the molecules. So according to their repulsion, we can determine the geometry, the molecular geometry. And the second part is about the dipole moments and the polar molecules. The third one is about the valence bond theory. And the fourth one is the molecular orbital theory. Okay. So from here we know in the same group they have similar electron configuration, similar electron configurations. Like in this group, all their valence electrons are NS1, and this is NS2. Okay, so we learned this before. Okay, so basically you can use the valence shell electron pair repulsion model to determine the geometry of the molecules. For example, we know how to write the Lewis dot structure. For example, for these two molecules, they have the same number of carbon, hydrogen, and oxygen, but they may show different geometries. For example, in this case, so how to determine its molecular geometry? So you can use this model to determine the molecular geometry. So in this model, so basically electron pairs repel each other whether they are in chemical bonds or unshared. So basically electron pairs, they repel each other. It is easy to understand because they have the same charge, right? We know the particles with the same charge, they will repel each other. So electron pairs, they will repel each other. Okay. And so electron pairs assume orientations about an atom to minimize the repulsions. So what does this mean? This means because in one molecule, the electron pairs repel each other. Okay, so the molecule try to form the geometry in which the repulsions is smallest. Okay, so this is about electron pair repulsion. Okay, have a short break.